Okay, in this video, this is the first of several videos that's going to deal with carbonyl alpha substitution reactions. Okay, so in this first one, we're just going to be introduced to the concept of enolization. Actually, we've been introduced before. Let me just point out the only previous reaction to this point that you've had that involves enols. And this is this reaction right here, where we're taking terminal alkynes and reacting them with water, sulfuric acid, and mercuric sulfate to generate methyl ketones, okay? And this proceeds by the enol. Remember in the discussion back there we said that this enol, if ever formed, would spontaneously convert to the ketone. And in most cases, these ketones and enols are in equilibrium, okay? This type of equilibrium we're going to refer to by the name of tautomerism. Tautomerism just means that we have isomeric compounds that are in equilibrium. Okay, that's what a tautomer means. You may recall in the early parts of the organic chemistry that there were a lot of discussions about resonance. It may be tempting to think of these two as resonance structures, but they're not resonance structures, okay? They're not resonance structures. Let's just remember that. And this is because they have different connectivity. Okay, here we only have 2 hydrogens. Here we have 3 hydrogens, and here we have a hydrogen on oxygen, and which is not present in the other side of this equilibrium arrow. So we cannot, therefore they cannot be resonance forms. Okay, so let's say we start with a ketone, and remember you may have been introduced to this nomenclature previously. This is not official IUPAC nomenclature. We're just going to call this alpha. Alpha is the carbon next to the carbon of interest, or the most interesting carbon, which I know that's in the eye of the beholder, but the carbonyl carbon would probably be the carbon of interest here. Okay, if we treat a ketone with acid or base, we speed up the equilibrium between ketone and enol. We don't really change its position. It's still heavily in favor of the ketone form over the enol form, but we just speed up the process tremendously. Okay, in organic chemistry, where these species enols and enolates become really useful is when they react with an electrophile. They almost always react with an electrophile at carbon. Okay, and this forms what we call an alpha substitution product. Okay, all right, so formation of enols and enolates is key to performing alpha substitution reactions of carbonyl compounds. We're going to find that not only do ketones and aldehydes do this, but later in this chapter we're going to see that esters do it as well. Okay, so here at the bottom of this slide I have stated the 3 basic facts. In most cases, keto-enol equilibrium heavily favors the ketone. The equilibrium process is very slow at room temperature and neutral pH, but it can be accelerated tremendously by adding acid or base. Okay, let's look at a few exceptions to this rule that ketones are more stable than enols. It is possible to have structural features in your molecule that will make the enol form more stable than the ketone. Okay, so cyclohexadienone, shown right here, is actually not as stable as its enol form, and you can see an obvious reason here. This is aromatic. And this is not aromatic. Okay, so we previously discussed how what an energetically stabilizing situation having an aromatic ring is, and one can appreciate that if you have an aromatic ring, it would be more favorable than if you don't have one. Okay, all right, 1,3-dicarbonyl compounds have a lot of enol character, and this enol character is highest for ketones and aldehydes, which is much higher than esters, amides, and acids. Okay. All right. Why is this type of system more subject, or why is the enol more stable in a 1,3-dicarbonyl compound? Okay. First, we're have partial positives kind of close to each other. This destabilizes this a little bit, but more importantly, we have this important stabilization in the product here. Okay, so when you look at it this way, this oxygen lone pair is engaged in a rather heavy-duty resonance interaction with the carbonyl group. Okay, we also have, in this case, a very strong intramolecular hydrogen bond. Okay. And these are very stabilizing structural features, this resonance interaction and the intramolecular hydrogen bonding, which tend to make 1,3-diketones more stable as enols. Okay? You can't always, depending on the geometry, you cannot always form this intramolecular hydrogen bond, but this resonance interaction is pretty much always present. Okay. Or as long as you can achieve that geometry there, you can have that resonance interaction. Okay, 1,2-diketone in many cases, we find that it's more stable as the enol, and again we have this intramolecular hydrogen bonding, plus we have the fact that having two partial positives right beside each other, like you have here, is a tremendously destabilizing structural feature, and that means that the enol isn't quite as higher, or isn't quite as unstable as it is usually. So there's a lot of enol present in 1,2-diketone systems. Okay, let's look at the mechanism for acid and base catalyzed enolization. Here's what's happening in acid catalyzed enolization. I'll just use H3O plus as my acid right here. Okay, so we're protonating at the carbonyl oxygen lone pair to give us the species here. Let me put the lone pair there. That would be more appropriate. Okay, so this gives us the protonated ketone, and what we do now is we remove the alpha hydrogen in essentially an acid-base reaction, and this gives us the enol. Okay. Again, this doesn't affect the position of the enol. It just affects the speed at which the enol is formed. Okay, and this can go back to the ketone by the reverse mechanism. Okay, we're going to find that acid catalyzed enolization isn't used in nearly as many of the reactions we're going to talk about as base catalyzed enolization. Okay, base catalyzed. Here's what's happening. We're pulling off the alpha proton. How easy that process is signified by its pKa value. Its pKa is about 20. Recall that water has a pKa of about 16. Okay, so when we pull the alpha proton off in this fashion, this gives us the enolate anion. The enolate ion is really just the conjugate base of the enol. Okay, and once this is formed, it can react with a hydrogen to make the enol. Okay, all right. Now, because water has a pK that's lower than the ketone, this means that this reaction here is actually the reverse of this reaction is more favorable. We're going to encounter many bases where this process here is just going to stop. It'll stop here. If we have a very strong base, okay? If we use a base much stronger than a hydroxide ion, we'll typically stop the reaction right there at the enolate phase. Okay, another important thing to point out here is that this is a resonance structure. By the rules of resonance that we looked at very early in organic chemistry, we would say that the resonance structure that I circled is not as good as the enolate ion resonance form. And that is in fact true. If you took a picture or an X-ray structure or whatever of this intermediate, you would find that it looks more like this, okay? Carbon-oxygen single bond, carbon-carbon double bond. But when we think about the reactivity pattern, this resonance structure that I've circled is actually more reflective of the reactions that we commonly see for these enolate anions. In other words, we react electrophiles with carbon. Okay? All right, so let's look at one of the fundamentally important acid-catalyzed reactions, and that is alpha halogenation. Okay, so it's common that we would treat a ketone, or these are the common conditions here. We would use acetic acid as solvent and just the halogen present dissolved in acetic acid. Okay, so bromine and acetic acid, if we treat this ketone with bromine and acetic acid, we're going to get the alpha bromo ketone. And as a byproduct, we make HBr. Okay, you can see here where we don't really have much in the way of acid in the very early stages of this reaction, but it becomes quite acidic as the reaction progresses. Okay, so we're going to make an enol. Our enol has a carbon-carbon double bond, and that's a species that we've seen react with bromine a lot of times before. Okay, so I'm going to write this mechanism here. Okay, I'm going to attack it at carbon. We could write a resonance structure where the lone pair stabilizes the carbocation, and this is probably the better resonance form. Okay, and we just remove this proton here, and that gives us the product. Okay, this alkene is reacting a little bit differently than we saw bromine react with simple alkenes. When bromine reacts with simple alkenes, we make a bromonium ion. And that doesn't happen here. Okay? And that's because this carbocation here has such strong resonance stabilization by the oxygen lone pair that there's no need to form the bromonium ion. Okay? Another thing that we also saw simple double bonds do is add a bromine, like here. Okay? And this doesn't happen. Even if it did happen, this is an unstable type of compound that would just spontaneously fall apart and make our products anyway. You can think of this as the bromine analog of a hemiacetal or a hydrate. Remember, those aren't stable either. Okay? All right, so here's another alpha halogenation reaction. This occurs with carboxylic acids by a similar mechanism. This is called the Hell-Volhard-Zielinski reaction. It's easy to remember. It's our only organic reaction that has a cuss word in it. Okay, so somewhere in Germany 100 years ago, there was a Dr. Hell walking around the chemistry building. All right, so let's look at how this is occurring. All right, so bromine and phosphorus is followed by a water workup will convert a carboxylic acid into an alpha bromo carboxylic acid. An important point to remember here is that very likely this combination of reagents is making phosphorus tribromide, which is, if you remember, PCl5 and PCl3 were alternative reagents for converting an acid to an acid chloride. Well, what's thought to happen here is that we make an acid bromide. This, under the acidic conditions, makes the enol. The reaction above occurs with the enol to give us the alpha bromo acid bromide. And, sorry, this is just reacting with water to make the alpha halo carboxylic acid. Okay, all right, so let's look at some base catalyzed enolizations. Okay, and a thing to remember here is your choice of base has a major impact on how you'll actually carry out these reactions. Okay, so the pKa of a ketone is about 20. All right, the pK of these species here, alcohols and waters, remember, these are less acidic than ketones. Okay, we're also going to look at using the conjugate base of this amine as a base, and this compound here has a relatively high pKa. The amine has a pKa of about 34, so its conjugate base is actually very basic, far more basic than a ketone enolate, and that's going to have a big effect on this reaction. So let's think about, in each of these cases, where does the equilibrium lie in each of these reactions? So let's look at the first one, hydroxide ion. Okay, hydroxide ion is the conjugate base of water. Okay, so remember that acid-base reactions proceed in such a way as to give you the weak acid, weak base pair. Okay, so if we look at the acid component, this is the weak acid. Sorry, no, okay, gotcha. This is the weaker acid. Remember that as the pKa numbers increase, we're looking at weaker acids. Okay, so this reaction goes heavily to the left. Okay, potassium T-butoxide is the conjugate base of tertiary butyl alcohol. Okay, now tertiary butyl alcohol still has a pKa lower than a ketone, but not much lower, so we're going to say that this reaction still goes to the left, but not as far to the left. Okay, so I'm going to just draw representative arrows that show a closer equilibrium, or equilibrium that's closer to 1 to 1. Okay, this is an important abbreviation to remember. LDA, lithium diisopropylamide. This is a very commonly used base in organic chemistry. Okay, so it is the conjugate base of something that has a pK of 34. So when you look at this reaction, this is the strong acid. All right, so the equilibrium is going the opposite way. Okay, it's going to the right. In fact, we can say that this arrow here is negligible. Okay, so this really isn't even an equilibrium at all. This just goes to the right. You just simply deprotonate it, and that's all you do. We'll find out that we never just do that. We add something else later. Okay, let's look at a important base catalyzed reaction, and this is called isomerization. Right, so if we start with this compound, cis 2,3-dimethyl cyclohexanone, and treat it with base, what we're going to find is that we isomerize from cis to trans. Cis goes to trans. Very interesting thing happens if you use deuterated analogs of methanol and sodium methoxide is not deuterated, so deuterated methanol gives you also the trans, but with 3 deuteriums in it. We'll call this D3. That's how the nomenclature for the deuteration process goes. So that's that compound D3. Okay, so how is this reaction proceeding? All right, so if we think about alpha hydrogens that we can remove, there's 3 of them. Okay, each of those 3 hydrogens I just drew is alpha to the carbonyl group. Okay, and in theory, any one of them can be removed. There's a slight difference in the acidity of these 2 hydrogens, and generally we say this is the thermodynamic enolate because it's more stable, and that's because it has the more substituted alkene. And this is the kinetic enolate. This is the one that you actually form first. You form this one first because this position is sterically more accessible. Okay, since that position is sterically more accessible, it's easier to pull off that proton. And so in this particular case, we have a thermodynamic enolate and a kinetic enolate. Okay, it's kind of, as a general rule, the kinetic enolate is the one that comes from removing the less acidic hydrogen, or more accessible, sterically more accessible hydrogen, but it's not always the case. Sometimes there can be extreme differences in the acidity. We'll see cases of that a little later in this chapter. Okay, all right. So what happens here is that when we make the thermodynamic enolate, we're going to add a hydrogen to this position. And when we have lots of deuterium, we put a deuterium there, right? Okay, and if we remove it, we can add this hydrogen or deuterium either to oxygen or carbon. It doesn't matter because we're going to do this many, many millions of times, or well, remember 1 mole is 6.02 times 10 to the 23rd atom. So we're going to do this a lot of times. And eventually, because we have this as the solvent, there's many more moles. Relative to the substrate, okay? All right, so because the number of methanol or deuterated methanol molecules heavily outnumbers the number of substrate molecules, we're eventually going to put deuterium in every position where we can remove a proton, okay? So the kinetic enolate can also add a deuterium by the same process. Eventually, all of the hydrogens that can be removed are going to be replaced by deuterium. Okay, so why does this reaction go from here to here? It's a simple principle, axial versus equatorial. Okay, so in the initial phases of this reaction, this alpha proton, this alpha methyl group is axial, or either that I'll say either the alpha methyl or the beta methyl has to be axial in the starting material. But when we do the isomerization, we get to a situation where where both methyl groups can be equatorial, and that's what's driving this reaction to equilibrium. Remember, at equilibrium or thermodynamically, we say that we're just forming the more stable product, okay? And the trans is more stable than the cis because the trans can exist as the diequatorial compound. Okay, so we're going to in this video right here, just by doing a predict the products of the reaction. Okay, so as with all these other videos, you should pause it right here, do it yourself, and then replay it and see the answers. I'm going to go ahead and give you the answers here. Okay, so we're going to treat this with bromine and acetic acid. Remember that if we were going to brominate in the aromatic ring, we would need FeBr3 or something like that. It turns out that probably wouldn't help us here either, because the enol that we form is far more reactive than the benzene ring, and this is the product that we would expect. Okay, here we're going to do also an epimerization. We have the cis compound. We're going to turn it into the trans compound. Okay. Notice how we isomerize right there at the alpha position. And the reason this goes is, again, because when we start this reaction, we have this conformation. And what we see here is that this ring is fused where one of the carbons is axial. That carbon right there is axial on this ring. Okay? And this carbon is axial on the other ring. All right, so when we do the epimerization, we generate the one where the two rings are fused completely equatorial, giving us only axial hydrogens. Okay, in this one, we're starting with the pure S enantiomer. The reagent here, is the same reagent in a OET ethanol. All right, so we don't have another stereochemical marker, but if we start with an enantiomerically pure compound, we're going to get a racemic compound by doing the epimerization reaction. There's no energy difference between the R and the S enantiomer, so this reaction, if it proceeds to equilibrium, is going to give us a mixture of both compounds. Okay? All right, the final question is kind of a trivial question. Why is compound A so much more acidic than compound B? Actually, the pK of the compound on the left is 12. All right, the reason for that has to do with something a much older concept called aromaticity. When you remove the hydrogen here to make the enolate, you get an enol, but embedded in this enol, of course, circled is, let me draw a more exact circle. This is a furan ring. A furan ring has aromatic character, so the fact that you're generating an additional aromatic ring here makes this reaction far more favorable. Okay? If we look at the simple cyclic ester, when we generate the enolate from that, all we get is this compound over here. And it's just like a normal enolate. There's nothing particularly exciting that happened to drive the reaction, like forming an aromatic ring. It's just like another enolate. Its pK is a little higher than what you saw with ketones, because this is an ester. We'll look at esters a little later in the chapter. At this point, I'm going to stop the video. Okay.